Hello guys, and welcome to this short introduction to flight. My name is Liam Sutherland and I'm one of the instructors at the VATSIM Oceania training. Today what we're going to be covering is some basic theory knowledge to aid you in passing your P2 rating on the VATSIM network. So some basics that we're going to be covering today will include the main four forces of flight that act on an airplane. We're also going to cover some center of gravity fundamentals as well as some stability fundamentals when it comes to loading the aircraft. And we're also going to cover some flight controls and their effects on the aircraft in flight. So let's get started. So we've got our small display plane coming across here. This is a Cessna 172, and for this video I will be using this as our demonstration aircraft, but this basic knowledge that I'll be teaching you will apply to all aircraft. Alright, so looking at our aircraft here, assuming that it's in straight and level flight, which assumes that the aircraft is not climbing or descending, and it's at a set airspeed, so it's not accelerating or decelerating. So we've got four forces acting on the aircraft at the moment. And these four forces are basically working hand in hand to keep the aircraft flying. So, starting with the first force, we've got thrust. Now thrust is generated in this aircraft by the propeller, which is at the front of the plane, and that is powered by the engine, and as that spins around, it pulls the aircraft through the air, generating a force called thrust. And this basically keeps the aircraft moving forward through the air. So moving on to the next force, acting upward, we've got lift, which is generated by the wing. Now, basically how the wing generates lift is by there being a lower pressure on top of the wing and a higher pressure underneath the wing. And this pressure differential causes the wing to rise towards the lower pressure, which in turn generates a lifting force. I'll go over this in a bit more detail in another video, but for now, this is a simplistic demonstration of how it works. Now the next force we've got is drag. Now drag is basically opposing thrust. Due to the airflow over the airframe, it generates air resistance, which wants to slow the aircraft down. Now when thrust and drag are the same value, it means that the aircraft is not accelerating or decelerating, which in turn means that it's holding a set airspeed. And basically, the faster the airplane goes, the more drag it's going to produce, and the more thrust that we're going to need from the engine to overcome that drag. Now, obviously, as we reduce in speed, the drag is going to decrease, but there's more knowledge and it goes into a lot more depth than this, but for now, just assume that as the aircraft generates more speed, it's going to increase drag, and as it reduces speed, it's going to have lesser drag. Alright, now on to the last force, which is weight, which is imposed by gravity. And this force is basically wanting to get the aircraft back towards the ground again. Now, the lifting force obviously is opposing weight and is keeping the aircraft in the air. Now, when these two forces are the same value, like thrust and drag, you'll find that the aircraft will not climb and it will not descend, otherwise known as the aircraft is in level flight. So that's basically the four main forces that we've got acting on an airplane in straight and level flight. There is a lot more detail to go into forces, especially when we're looking at an aircraft that's climbing or an aircraft that's descending, as well as an aircraft in a turn. But these are much more thorough explanations, so these will likely come into another video associated with a higher VATSIM pilot rating. Alright, so we'll now move on to the next fundamental, which we're looking at, and this is center of. So looking at our display plane here again, we've got the aircraft just flying, assuming that it's in level flight, or we can assume that it's on the ground. It doesn't really make a difference. but assuming that the background's blue, we'll assume that the aircraft is flying. Now, when we're talking about center of gravity is basically a point where all the weight through the aircraft acts through. So if we bring up the center of gravity symbol here now, you'll see that this symbol now represents the center of gravity location for this aircraft. Now, the center of gravity is where all the weight in the aircraft acts directly down towards the ground. So the reason why the center of gravity is further forward and not in the center of the plane is because we've got a heavy engine in the front, as well as the people sitting in the front as well, and we've got avionics and all the generally heavier stuff in the front of the aircraft, which means that the center of gravity is going to tend to be forward of the center of the aircraft, as it is in this example. Now, when we're looking at loading an aircraft, the center of gravity will change depending on the loading. So, for example, if I was to add 180 kgs of passengers and baggage in the back of the plane, that's going to create a downwards force, obviously, and that result of the weight in the back of the aircraft is going to mean that the center of gravity is going to tend more towards that weight. So when we're adding fuel into the airplanes, which in this plane is stored on the wings, it'll also have a more of an effect on the center of gravity and move that correspondingly to how much weight you're adding in a certain location. So obviously, as you add more weight, depending on where it is in the aircraft, if it's further aft of the aircraft, which is towards the rear, the center of gravity will move a bit more depending on the weight in that area. Whereas if I were to add some more weight in the front passenger seats, then you'll notice that the center of gravity will move, but it will not move quite as much as if you've put the same weight in a location slightly aft of the aircraft. So that's basic fundamentals of the center of gravity. But now we're going to move on and we're going to look at how longitudinal stability acts on this aircraft. So we'll move on. So if we're looking now at the center of gravity's effect on the aircraft stability, we'll see that if we bring up our center of gravity again in the same location, slightly towards the front. Now, remembering that when I discussed the previous example, that weight acts through the center of gravity. So the whole weight of the aircraft will act through the center of gravity while it's in flight. Now, we've shown weight, but what we also need to consider is where the lift force is acting. And in this case, we'll assume that the lifting force is as where this arrow is showing right now. And CL stands for the coefficient of lift, or the center of lift. So in this case, this is where the lifting force is acting on the wing and on the aircraft. Now, if we're looking at this example here, basically if you picture the aircraft in flight, it is hanging off the center of lift. The center of lift is what's pulling the aircraft up in the air. So if you can imagine that the center of lift, that there's a string connecting through the center of lift to the wing, and you're holding the aircraft and dangling off a string. Now if you have a look at the center of gravity, you can see that the center of gravity is forward of this center of lift. So the resultant of this will mean that because all the weight is acting through the center of gravity, you'll find that because there's a little bit of distance between the center of lift and the weight, that the aircraft will tend to nose down, as you can see here. Now to counteract this, we obviously have an elevator at the very rear of the aircraft, and this elevator will generate a down force which counteracts this nose down pitch and will allow the aircraft to stay in level flight. Now if I go back, it's not going to let me go back, that's bad. So we picture that again, and the center of gravity was forward of the center of lift, Now the aircraft is going to be inherently more stable because if you think of the aircraft when it stalls, which is when the aircraft no longer has enough airspeed to maintain the required lift to overpower the weight of gravity, the aircraft is going to stall and no longer be able to maintain level flight. So when that happens, because the center of gravity is ahead of the center of lift, what's going to happen is once the aircraft stalls and the elevator doesn't have as much effectiveness, the nose is going to drop, allowing for the airspeed to rise and you to recover from the stall. So at the state that the aircraft's in with the center of gravity ahead of the center of lift, we'll observe that the aircraft is longitudinally stable. And that means that basically the aircraft is a lot safer than it was than in some of the other configurations of the center of gravity, which I'll show you in a minute. There is a disadvantage for having longitudinal stability, and that is being that because the center of lift is because the center of gravity is ahead of the center of lift, we have to have this elevated downforce that you can see here. And because of this elevated downforce, the wing has to produce more lift to be able to counteract this elevated downwards force. And in generating this more lift, we're going to have a higher angle of attack, which means we're going to have more drag. So the downside of having the aircraft in a stable state where the center of gravity is ahead of the center of lift is that the aircraft is not going to fly as fast. But I'll show you why it is much safer to have the center of lift and preferred to have the center of gravity in front of the center of lift. Let's move on. Here's our center of gravity now. It's slightly aft. Now you'll see that obviously what would cause the aircraft to have the center of gravity in this position would be potentially some people in the back, maybe the tanks are full of fuel, and this will cause the center of gravity to move aft. Now if we know that because weight acts through the center of gravity, that roundabout with the center of gravity as it is, it's going to act about the same position as the center of lift in this case. So imagine again that the center of lift is a string holding the aircraft up, and the weight is acting down through the center of gravity. Now, if the center of lift is a string and you're dangling the aircraft in the air, you'll notice that the aircraft will just stay level. It's not going to pitch down, it's not going to pitch up. It'll just stay in the position that it's in. Now, this aircraft is partially stable, but it's not as stable as it was when the center of gravity was ahead of the center of lift. And the reason for this being is that when the aircraft comes to stall, the aircraft is not going to be as readily wanting to pitch down with the nose. And basically this means that we're going to have to generate some downforce on the nose, or some upforce on the back of the plane to bring the nose down to recover from the stall. Now, in a stall, because the airspeed is very low and the elevator at the back of the plane loses its effectiveness at this lower airspeed, it's going to be a lot harder to bring the nose down, which means that inherently it's going to take longer to recover from the stall, and it's not a good situation to be in, especially if the aircraft is low to the ground, where you really want to recover in as least altitude as you can. Now, obviously, because the center of gravity is in line with the center of lift and we're not having to generate a force on the elevator in this case, we are able to have the aircraft cruising at a higher speed. But the trade-off is that obviously the aircraft is less stable. Let's move on and bring the center of gravity now further aft, as you can see here. Now, weight's acting through the center of gravity as it usually does, and we've got our center of lift. Now, problem here being the center of gravity is now aft of the center of lift. And this presents a major problem when it comes to stability and flying the aircraft. Now, if we put the aircraft in this state, obviously if you're hanging the aircraft through a string again through the center of lift, you'll find that the aircraft has a tendency to want to nose up. I'll show you this in a second. And obviously we're going to have to produce an upwards elevator force to counteract this to keep the aircraft in level flight. Now, because the elevator is supporting some of the weight of the back of the aircraft will cruise faster because the wing is not having to support as much load. But the trade-off, as I said before, is stability, and this I'll show you right now why it's very dangerous to have the center of gravity in this aft position. So imagine the aircraft is flying along, and let's say you get busy with some stuff in the cockpit and you're on approach to landing. So you're fiddling around with stuff in the cockpit, you're at a slow airspeed, and you're quite close to the stall. Without noticing, the aircraft begins to stall, and you suddenly realize that the aircraft is stalled, and what a silly mistake you made to get distracted in the cockpit. So when the aircraft stalls, because the elevator loses effectiveness, not completely, but it loses some effectiveness at this lower airspeed, we'll observe that the nose, obviously you've got your elevator force and that'll reduce, the nose will come up as the aircraft stalls. Now, because we need a nose down attitude to gain airspeed to recover from a stall, with the center of gravity after the center of lift, the aircraft is not going to want to nose down. It's wanting to stay with the nose up because remember that string attached to the center of lift on the wing, and the center of gravity is aft of the center of lift. The aircraft wants to nose up, and because of that really low airspeed in the stall, and the elevator has lost a lot of its effectiveness, it's going to be very hard, if not near impossible, to lower the nose of the aircraft. And this will result in the aircraft pancaking into the ground or even entering a flat spin, which is not a good idea at all and is a very dangerous situation. So from these you can see that the trade-off for stability is speed, and basically you really want to have your center of gravity ahead of your center of lift if at all possible. Otherwise you're endangering the flight and potentially risk crashing the aircraft. So it really depends. If you're wanting to get more speed but the aircraft being less stable, then it's not a good idea. I mean, it's only going to be, depending on the aircraft type, say in the Cessna 172, you may get an extra, say, 10 knots on top of the cruising speed when the center of gravity is further aft. But for your peace of mind to have the aircraft in a condition where it's ready to recover from a stall, and you're less likely to pancake into the ground or enter a flat spin, for example, it's much safer to have the center of gravity ahead of the center of lift, and a better idea, as well as airmanship, to show the responsibility as a pilot to keep your center of gravity within its limit. Okay, let's move on. So now we're going to look at the elevator. So at the rear of the aircraft, as we were discussing before, the elevator provides a down or upwards force to keep the aircraft in level flight, or the nose attitude that the pilot requires during a given stage of flight. So in this example, you can see that the movable elevator surface is represented by the green triangle on the elevator at the rear of the aircraft. Now, if the pilot was to pull the control column towards himself, as in to pull the control column back, the elevator will move up, as you can see in the example here. Now, when we bring some airflow into this, you'll see that by doing this, the elevator deflects the airflow and creates a downwards force, which in turn will bring the nose of the aircraft upwards. Now, this stands true as well for the opposite control movement of the elevator, which is pushing the control column forward, and the elevator moving downwards, meaning that the aircraft's nose will pitch down. Now, there's secondary effects when it comes to this control movement. So when you're raising the nose of the aircraft, because you're climbing and because of the way that gravity works and the weight of the aircraft, we're going to have some weight as the aircraft's at a higher nose attitude displaced behind the aircraft. And what that'll do is also add to the drag force on and basically increase the drag or weight force on acting rearward of the aircraft while the propeller or engine is still producing the same amount of thrust. So by pitching the aircraft up and climbing, you'll observe that the aircraft will slow down. So the secondary effect of pitching the aircraft up is to see the airspeed slowly decrease. Now this is sort of similar to when the aircraft descends, except because we're heading towards the ground and the way that gravity works, it's adding to the thrust component. And in this example, then you'll observe that pitching the nose down will increase the airspeed of the aircraft. So these are the secondary effects of what we call pitch. And pitch is just another term for the attitude of the aircraft, which is pitching the aircraft up and pitching the aircraft down. So the secondary effects of climbing is the airspeed will decrease. The secondary effects of descending or pitching down will be that the airspeed will increase. Alright, let's move on to the ailerons now. And you'll see that the up here, just like that. Alright, ailerons. Now ailerons are located on the ends of the wing, and what the ailerons are used for are to bank the aircraft or roll the aircraft. In this sense, we call when the aircraft turns left or right, we call this roll. Now, the ailerons work similar to the elevator, and I'll show you how. So you can see that the green triangle on the end of the wing here is representative of an aileron here. So if I were the pilot, if I move the control columns to the left, you'll observe that this aileron on the left wing will move up. And when we introduce airflow over this wing, and you'll observe that the aileron deflects the air upward, we'll get a force acting down, which will pull the wing down. Now, this is kind of a weird angle to look at this demonstration from, which is why I'll show you another angle in a second. So hopefully that'll make sense to you guys that because the aileron is coming up, it is reducing the amount of lift on that left-hand wing, and basically it's making the wing go down. So let's change to the other angle and we'll show you how this works. So looking at the back of the plane, we've got our two components of lift on each wing, which is just representative of the lifting force on each wing. Now, if we were to move the control columns to the right, you'll notice that the left aileron will come up and the right aileron will go down, as you can see here. Now, the left aileron is going to deflect air upwards, while the right aileron will deflect air downwards. Now, as I said before, that the aileron on the left wing, as it comes up, it's deflecting air upwards, which is decreasing the lifting force on the left-hand wing. However, because the aileron on the right-hand wing is deflecting air downwards, it's adding to the lifting force on the right wing. So the lifting force on the right wing will increase. So, you've got the aileron force, as you can see there. And because if you add the aileron forces to the components of lift, you'll observe that the left wing, the component of lift will decrease, and the component of lift on the right wing will increase. Now, as a result of this, it means that the right wing wants to climb, whereas the left wing wants to descend. And what this causes is a rolling effect to the left. You'll note that the aircraft will roll left. And this is the basic fundamental of how ailerons work. And the same for if the aircraft was to turn right, you would move the control column to the right. The ailerons on the right wing would come up, and the ailerons on the left wing will go down. Now, secondary effects of the aileron include not just the aircraft rolling, but when we're rolling the aircraft, what we also get is a secondary effect called yaw. Now, when the aircraft yaws, I'll explain yaw actually in the next slide, but when the aircraft banks, what it does is it skids into the turn. So I can't really show this in this diagram, but just bear with and try and imagine to what I'm trying to say and explain here. So the aircraft will roll left, and as it rolls left, it kind of skids left and skids into the turn. Now, I can show this with a bit of a drawing here. So if I get my pen out, so the aircraft is going to skid this way as it goes into the turn. Now what this is going to cause is the aircraft's nose to pitch to the right. Not pitch to the right, sorry. Well, sort of pitch to the right, but it's going to yaw to the right. And by yawing to the right, it means it's going to be skidding through the turn, which isn't as efficient. Now, I'll explain this in the next slide what yaw is, but this is the secondary effect of bank, or roll, is yaw. Let's move on. Looking at the rudder now. So the rudder, you can see, is represented by the triangle, the green triangle on the rear of the aircraft here. And basically, the elevator is below it, and that's a horizontal surface, and the rudder is a vertical surface. As in, just imagine a wing that's just going straight up. Now, when the the rudder is in the neutral position, it's not producing a force left and it's not producing a force right. Now, if you were to, as the pilot, push on the left rudder pedal, you'll see the rudder will move to the left, and as a result of this and the airflow going over it, you'll notice that the airflow will be redirected to the left as well. And this will create a force which is generated by the rudder to the right, and you can see this here. And because of this, the tail of the aircraft will move to the right and the aircraft will move left, which is what we call yaw. Now, in a turn, like I was saying before, the aircraft will skid into the turn, skid out of the turn, sorry. And to keep the aircraft in balance, which I'll explain in another video, we'll add some left rudder in that left-hand turn to keep it in balance around the turn. And I'll explain this again, like I said, in another video. Now, rudder also has a secondary effect, or yaw as we call it. Now, the secondary effect is when you, say, push the left-hand rudder pedal as I have in this example here, you'll notice that as I push left on the left rudder pedal, the aircraft will obviously yaw to the left, but the secondary effect of yaw is roll. So as I push left on my rudder pedal, the aircraft will yaw to the left, but it will also a little bit, not a huge amount, but it will also roll a bit to the left as well. And that's the secondary effect of the rudder, or yaw. Now, so in conclusion, we've covered the 4 forces of flight, which include lift, thrust, drag, and weight. We've also covered the center of gravity and its effects on the aircraft when it comes to adding loading or weight in different parts of the airplane. Also covered longitudinal stability, and that is related directly to the center of gravity position. So if the center of gravity is ahead of the center of lift, the aircraft is stable, whereas if the center of gravity is closer to the center of lift or aft of the center of lift, the aircraft will be less stable. We also covered the basic control surfaces, which include the elevator, the ailerons, and the rudder. And from these basic control surfaces, we learned their secondary effects. We learned that also for elevator, that what we call that is pitching. What we call roll, when we use our ailerons, we call that roll. And when we use our rudder, we call that yaw. Now the secondary effects of these, as I stated before, include with the elevator, if the aircraft climbs or pitches up, the airspeed will decrease. If the aircraft pitches down and descends, the airspeed will increase. With ailerons, if we make a left turn and roll them to the left, we'll notice that we'll get a yaw out of the turn. The aircraft will have to have some rudder input to be balanced around that turn. And for rudder, as we put in rudder, let's say we put in left rudder, the aircraft will also bank in the direction that you're putting rudder into. So if you're putting left rudder in, the aircraft will yaw to the left, and it will also slightly roll to the left as well. Alright, we also, like I said, covered pitch, yaw, and roll. So I hope you guys learnt quite a bit in this video. It's definitely some of the knowledge that you will be questioned on when it comes to gaining your P2 rating on the VATSIM network. I hope you enjoyed this video, and if you need any help, feel free to contact any of your instructors and we'll be happy to help you out. As again, my name is Liam Sutherland. I enjoyed showing and presenting this to you. I hope you learned something, and we'll see you all on the next video.